we can have also other kinds of model. It's gonna be an hands-on course. So the idea is that, well, this is gonna be a theoretical course, but the idea is to study certain number of applications which are dealing with physics, economics, biology, everyday life, and so forth and so on. You're old enough to be critical about university course. So I have my idea for the structure of this course, but I'm extremely open to new ideas. So if you would like to explore one direction rather than another direction, please just tell me. You can send me an email, and I will be happy to fix the things, to change things in order also to meet your ideas and your desires. So just few comments on the course. So we're gonna have 2 lectures per week, 2 hours today, 3 hours on Tuesdays. For those that are at home, there will be some limitations. So we're limited to something like 18 students in this classroom. As far as I know, you should be able to book, to reserve a seat here in the classroom if you want. But today there are 2, 4, 6, 7, 8 guys here. So in total we are 38. So take into account this. This year I don't expect to do any kind of introduction to numerical methods. Okay. In principle, I'm thinking to do this for next year, but the idea is that for this year, I'm just limiting to the theoretical part plus exercises. If you have one of the desires I was speaking about before is something like, let's try to work a bit with Python or Mathematica or Maple, happy to do that. Don't ask me MATLAB because I don't know MATLAB. At the moment, I'm not very good with MATLAB. Regarding the exam, don't know how many of you are starting this Laurea Magistrale, this course, this 2 years course, especially those that are following at home. Basically, I think that all you guys who stand here in the classroom, you have already done the 3 years here in Savona, right? Okay, great. So you know how the structure of the exams in Italy is. The Italian system, for those that are at home and are foreigners, the Italian system is probably unique in the world because the final mark is expressed in 50s. So the maximum mark that you can get is 30, and the minimum mark is 18. So the important information for all of you as well is how the exam is going to work. So I was thinking about 2 possible routes, possible ways to do the exam. The first one is let's say the traditional one. So basically the idea is to have some written exam with exercises and stuff like this. The exercise is gonna be, how much did you run? 3 hours. 3 hours. 3 hours, and in order to pass the exam, you should reach a minimum of 15 points on 50. And then after the written exam, the written test, there will be the oral exam, which is gonna be around 50 minutes or so, or even less, with well, the usual thing, question and answers on eventual mistakes in the written test, and something else in the program. There's another possibility, another way, which could seem easier, but pay attention because it's not easier at the end of the day. So the idea is to write the report. So you can do the following. You can identify any phenomenon you are interested in. You can be interested in distribution of leaves on trees. That's fine. You are speaking with me. You are arranging with me, and we're reaching an agreement about the topic that's going to be the topic of your report. Then you write the report. In which sense? You are describing the phenomena, you are describing the mathematical model which is behind this phenomenon, writing the equations, studying the equations, eventually finding the solution if you're able to find the solution. And then you submit this report, and well, after a couple of weeks or something like that, we can have a presentation of your report with another time the answer and question session. Again, I don't think that this is easier than the first route. It can be probably even more interesting than the first route, but it's not a trivial exercise. Let's put it this way. About me again. A few years ago, I used to be available 24/7. So 24 hours, you could write me, and I would get answered in few minutes. Actually, unfortunately, it's not. Unfortunately, it is not so anymore because I have a toddler, a 2-year-old toddler. So I'm trying to answer as fast as possible, which probably I can. If you write me an email, I'm able to answer in 1 day or 2. In any case, I'm going to be available for speaking with students here in Savona between 4 and 6 p.m. on Mondays, and eventually, if somebody is from Genova, also from 10 to 12 on Fridays. Yeah. In any case, it's better if you contact me and to my email address, which is this one. Vincenzo.vitagliano@unige.it. Yes, this one. And what's the very last thing that about this short introduction is bibliography, right? The bibliography. So, guys, I'm extremely happy to upload my notes. These are handwritten notes, okay, and they are, well, I think that they are understandable, but it's up to you to judge it. However, I'm following in a very close way the book by Bellomo, De Angelis, and Dell'Itala. So it's, come on. And the book is lecture notes on mathematical modeling from applied sciences to complex systems. Believing that my handwritten notes are better and better than this. It's actually difficult to write with this. From applied sciences to complex systems. Actually, it's not math, it's mathematical modeling. Mathematical. And guys, this is, you can find this book for free on internet, legally. So you can download from. If you Google it, you're able to find. Pay attention because actually there are two different versions of the book. One which is from 2007, something like this, but this one is from 2010. If you have any difficulties in finding and downloading book, write me an email, and I'm extremely happy to pass the book. Actually, I cannot. I think that I cannot put the book directly on the OneNote because probably this would be illegal. But in any case, this is a file which is provided by the authors. So you can download it and it's gonna be fine. This is the most important textbook that I'm going to follow, but there are a number of other books that I will use. For those that I will use, I will then well, I will tell you as far as we are introducing these concepts from these other books, and then what are the other books? There is a book by Strogatz, which is non-linear dynamics and chaos. Well, also there are several versions. Last version is from 2018. This is actually not free, but I think that you can find in the library, or if you don't find it in the library, again, you can ask me, and I will try to understand how to do. Actually, this is a very nice book. This book is mainly on dynamical systems. But this guy, believe me, this guy is a genius. Strogatz is a genius. He's the best applied mathematician of the last century, probably. And even if you don't know, probably you are using things that are being developed on top of his models. Because he started with a PhD working on what's in English? I think it's circadian cycles, cicli circadiani in Italian. So have you ever heard about this thing? It's basically no. It's the alternance of sleeping time and awake time in the life of a person. Okay, so this guy, applied mathematician, starting with the model on this, and moves to model. And he's famous for these models of the fireflies. Fireflies rhythm of lighting around. But he's mostly known for a couple of papers, which, as far as I know, are among the top 10 most cited papers of the last 20 or 50 years, because he developed the theory of small network in internet, Google, Facebook, and all these things. Yeah, and probably it's for this reason that it's mostly known, most well known. In any case, the book itself deserves to be read even without the idea of studying it, because it's a nice book. Then there are another couple of books which instead are technical ones. One is from Farlow. Is a name. And it's partial differential equations. I'm writing JSPDs for scientists and engineers. This is an old book, 1982. And finally, the very last one, which is from Beltrami, Mathematics for dynamical modeling. This is also 1987. All right, but again, mostly if you are downloading this thing, probably you will find everything here inside. And as far as I'm using something different, I will tell you. And if you don't want to read any other book, it's enough if you're just taking my notes and trying to understand my notes. Okay, great. And if you do not have any objection on this part, and I hope that you don't have anything to say about me or about the structure of the course itself, we can pass to the first lecture. So we're going to discuss what is a mathematical model. We're going to see first ideas of mathematical model. And I will give some simple introductory definition that we will use in in the entire course, basically. So, what's the idea of what's your idea of mathematical model? What's for you a mathematical model? Somebody which is a bit bit of college. I try to be as informal as possible. So I expect that you also be a bit more open to discuss this thing. What's your opinion? What's your idea of mathematical model? What's a mathematical model should do?
For example, take an object on an event to simplify it in a question, for example, a question that can explain the behavior in the time of this event or this object, the behavior with an external force, for example.
That's actually the content of the first lecture. We can also we can already go home. That's very good because that's exactly the idea. So the idea is that I'm starting from something which has nothing to do with mathematics, with something that I can see, that I can smell, that I can touch, which is which can pass through some phenomenological and empirical observation and experiment. And then what I'm doing is trying to translate this into some mathematical statement. Mathematical statement that can be an equation or a system of equations or wherever. So the idea is that, well, we have a kind of a number also of logical structure, computational methods that are behind and that can allow you to describe this phenomenon, these things that you can observe. So some of these mathematical models are supposed to be explicative, some others are not explicative. Explicative means that you can take a phenomenon, trying to find a mathematical description of this phenomenon, and this would be breakdown in some kind of simplifying equation which allows you to describe that phenomenon. This is basically, for example, what happens for the motion of planets. In order to study the motion of planets, what you are doing, you are going there with your telescope, you're observing with your telescope the planets that are moving, you say, wow, they are very complicated now, they are moving, they look very complicated. The idea instead is that you are able to summarize all this movement, all this motion of the planets with few equations that are some basic equations. Indeed, we can show that, for example, the third law of Kepler, which tells you that the square of the period of a planetary orbit is proportional to the cube of the semi-axis of the ellipse on top of which the planet is moving. Well, this law can be found directly from very basic mathematical structure, which are Newton law, F equal to m times A, and the inverse law of gravitation. So the fact that the modulus of the force is proportional to 1 over r squared. So if I'm taking these two things from one side, F equal m times A, and then the inverse law of gravitation. So this is G times the two mass, the mass big L, capital M and small m. So suppose that M is the planet which is orbiting around some body capital M divided by r squared. So consider for simplicity that you are considering a circular orbit, okay? But if you want, it's a kind of ellipse which has collapsed to a circle. So if I have a circular orbit, then I have the central mass m, and then this is more or less a circular orbit with small m. Hello?
I'm here.
Yes?
The first time.
Yeah, so what?
So,
Hello? You say that they are. Don't worry if you're late. You can sit down. That's not the problem. Come on. So, so the mass, the small m, will be subject to centripetal forces. Correct? So we know what's the centripetal acceleration. This tells me that the acceleration, centripetal acceleration, to which the mass small m will be subjected, this is equal to v squared over r, where v is the velocity. So basically, m times a, come on, m times a, the second law of dynamics is this one, correct? What I can do in order for the planet to be in equilibrium on the orbit, these force must be equilibrated by the gravitational force. So on the right hand side, I can write G capital M small m divided by r squared. Right? Now, if I have a planet which is moving on this circular orbit, I know how I can define the period. What's the period? Let me write the period as a capital P. The period is basically the time needed for the mass m to do one entire orbit, right? So it's that time that multiplied by the velocity v of the planet is giving me the entire orbit, which is 2 pi times r. Okay? So from this, I can easily recover v equal to 2 pi r over p. Then I'm using this expression here, in this equation here, such a way that I can write, yeah, that's correct. I can write this as 4 pi squared times r over p squared times m equal to capital G, capital M, m over r squared, right? Now, what I have to do is just to isolate p on one side and r on the other side. So I can write this as 4 pi squared, and then I can simplify this thing, divided by G times capital M times r cubed. These are numbers, it doesn't matter, just numbers, equal to p squared. So basically what
Capital P is the period that planet need
To do an entire circle, to entire order.
around the hem, the capital M body.
Yes, that's exact. That's basically the time that you spend for doing this entire
Okay.
to run on this entire cycle. Then the idea is, but at the end of the day, the idea is that doing with this kind of simple exercise, what I will find is this law here. I don't care about this number, wherever it is. I can also write this as some number alpha. What is important is that using just the second law of dynamics, Newton's second law of dynamics, plus the law of gravitation, actually the law of the inverse law of gravitation. So modulus of the force equal proportional, inversely proportional to the square of radius. What I will find is this kind of relation, which tells me that p squared. Guys, somebody has the microphone open. Somebody at home has the microphone which is open, please. All right. So what's important is that the period, the square of the period, is going to be proportional to the cube of r. Okay? Guys, this is exactly the third law of Kepler. Third law of Kepler tells you that p squared is proportional to the cube of the semi-axis. In the case of Kepler, well, you have something which is a bit more complicated because you can have this ellipse. So A is the semi-axis of the ellipse, and then the period is going to be proportional to the semi-axis. But if you shrink the ellipse to a circle, the semi-axis is exactly the radius of this circle. Then you will have the Kepler's third law written for a circle. So all these things to say that this kind of theory is explicative in the sense that allows you to reduce to basic equations and to follow eventually the behavior of your system. It's not definitely sure that any kind of mathematical model that you can think about is explicative. For example, there is a model which is extremely used in economy, which is the Black-Scholes model. Now, the Black-Scholes model, it's a model that tells you that it's basically a model which allows you more or less to have an idea of what's going to be the price, the stock price, the evolution of stock price in markets, azioni. So the idea is that the percentage difference between tomorrow's stock price and the stock price of today is something which can be described with some log-normal random variables, which basically means it's a kind of probabilistic distribution which is whose logarithm is following a normal distribution. Now, it's very, very complicated things for saying that possibly this kind of model is not telling you how the price is changing. Okay, it's just telling you that more or less it's following this kind of distribution, which does not mean that the model is not working because banks and people are making millions of euros and dollars with these models. That means that it does not give you an explanation of why the price is changing in one direction rather than the other direction. The important thing in any case for any model, whatever it is explicative or not, is that the model must be predictive, because a mathematical model which is not predictive is completely useless. Predictive means that the model must give you quantitative prediction. Now, the Black-Scholes model, if people are making millions with the Black-Scholes models, means that the Black-Scholes models works in terms of quantitative prediction. I'm taking this thing, I'm having some quantitative prediction, which in any case I have to fine tune because the model is not exact. Then I'm taking this thing, this model, I'm changing some parameter, I'm adding some other term, and I'm trying to be as close as possible to the reality of the evolution of some stock price. Another example, which instead is very precise, is the discovery of again planets, Uranus and Neptune. Uranus and Neptune were not discovered telescope another time. They were discovered because there were things that were not working. So astronomers were looking to the orbital motion of other planets, and they said, "Oh, come on, this planet should be here instead of there." But if I'm observing the other planet, I'm observing it in a different position. Why? Because there is this the orbit of Uranus and Neptune are disturbing the orbits of the other planets. Since I have a mathematical model which is working correctly for all the other planets, what I have to do is just to try to fit the parameter and try to understand why the things that I'm observing is different from the calculation that I do. If I'm doing this thing, what I discovered is that there should be other two bodies in this solar system, which allows me to have exactly the orbit that I'm observing for the other ones. And they discovered Uranus and Neptune. So most of the there is another distinction about mathematical models. So most of the mathematical models follows either a deterministic approach or a probabilistic approach. The idea of having a deterministic model is basically the idea that you are starting from certain data from the beginning, and then following this data with the equations that I have for my mathematical model, I'm able to arrive to a certain result which is going to be always the same. I'm starting from some data, X, Y, and Z, and then I'm evolving my data through the equations that I have for my mathematical model, and the answer is going to be always the same. Done. Okay? This kind of model are said to be deterministic. There are other kind of mathematical models instead, which are called probabilistic. They are called probabilistic because basically wherever is the initial condition that I'm starting, with which I'm starting to study my problem, the equation which are driving the evolution of the system are such that the final answer of this evolution will follow some probabilistic distribution. Okay, so the idea is that the mathematical model allows you to find the probabilistic distribution, which means that the final outcome will follow the probabilistic distribution, but you are not allowed to know what is exactly the answer, because of course it's just following this probabilistic distribution. Anyway, most of the models that we are going to study are deterministic mathematical models. So for the moment, you can also forget about the distinction if you wish. Now, the idea for today is to start by introducing a couple of very simple models to see. These are mechanical models, one mechanical model and another one which is for the derivation of the equation. Very possibly you have already seen both. But in any case, it's instructive to understand how does the process of modeling a system work. So for the first example, I want to consider a system which is given by some body connected to a spring and which is lying on some ground. So there is no friction. I'm supposing that there is no friction here in the between the body and the ground. The spring is a perfect spring, it's not dumping. So the this body here, the location of the body is determined by the location of its center of mass. So the body has some mass m. The localization then is the localization of the center of mass, which is going to be given by some coordinate x, and supposing that the origin of my system is here in this point here and 0. So x is basically measuring this.
Minus time k and x.
Say it again.
Is energy potential of elastic.
Is energy?
The energy potential of elastic.
It's a spring. It's elastic. It's an elastic force. Yeah. The idea is that we are going to use the elastic force. Yeah. But this x is actually the displacement from the origin to the place where the body is. So it's this distance here. Okay. All right. Then the second law of dynamics, Newton's law, tells me that force must be equal to m times a. So that's m times the second derivative of x of t with respect to t squared. Okay? On the other side, I know what this is equal to. As your colleague was saying before, this is related to the elastic force of the spring, which here there is the empirical part. So the process of writing down a mathematical model starts from the empirical observation. Because otherwise, I could not know what to write on this on the right hand side. What's the force with which the spring is acting on the body? What I'm doing is going there and then doing an experiment and observing and measuring what's the force, how the force is acting on this body. And I discovered that this thing is equal to minus k times, let me write delta x. This is minus k times x minus x naught. Here, k is some number. It's a constant, which is measuring how elastic is the spring. X naught is the rest position of the body. So it's the position in which the spring is not acting with any force. And this allows me then to write finally my equation for these systems, which is m squared x in that t squared equal to minus k x minus x naught. But then what I can do is to redefine an x tilde, for example, which is equal to x minus x naught, and to write this equation as m the squared the x tilde in that t squared. Why? Because the second derivative of x naught is equal to 0. X naught is a constant, so I don't care about that. Equal to minus k x tilde. Right? And this is the mathematical model which is determining what's the evolution of this kind of system. Just a very brief parenthesis, because it's something which I really love and I like to tell this story to students. So probably you have seen this in your class of physics 1. This is the law of Hooke, right? Hooke's law. But the funny thing is that, well, in the past, all these guys used to write these nice books with a lot of of drawings and a lot of funny things. Actually, Hooks, when first introduced his law, well, the law for.
There is another name for the law of Hooke.
What is another
The
name?
law of damage. Exactly.
Of what?
Damage.
Damage.
Yes, there is another law for Hooke for the damage.
Ah, I didn't know. Okay, interesting. I didn't know. No, well, but the thing is that if you're going in the book of by Hooke, which is from the 1675, so you can find this thing when he's trying. I think that's correct. Huh? So is at the end of the book. Actually, the book was speaking about something which is completely different. It was describing some experimental apparatus for a completely different thing. But if you're going to the appendices of the book, in the appendices of the book, you find the most interesting thing of these books by Hooke, because basically he's during those times, there were a lot of fights between scientists. I found something before of you, so this is my law rather than your law, and blah, 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 blah. So this was something like, if you are a musician and you send to the, you produce a CD and you want somebody not to copy your CD, what you're doing? You are trying to recording this officially with some institution, correct? So basically this guy was trying to do the same thing. He was saying, I discovered that there is some very nice relation between the displacement of a spring and some constant of the spring and the force that the spring is acting, which is acting on the body. And this law is going to be described by this thing. This was an anagram. So if you were patient enough, you can solve the anagram. Otherwise, you would have had waited 3 years, 1678, when the guy solved the anagram, and this is ut tensio sic vis. So for those of you that know Latin, this basically means tensio. Tensio at the time was basically referring to this displacement with respect to the rest position. So the force with which the spring is acting on the body must be proportional to the displacement with respect to the rest position. It's this thing here. Okay. Well, okay, it was just some curiosity. Back to our equation, which is d squared x that is squared equal to minus kx. What can we say more? Well, we can identify some vector variable u whose components are u1, which I choose to be x, and u2, which I choose to be the x in the t. Because if I'm doing this way, what I can do is to reduce my problem, so to reduce this mathematical equation to a linear system of two coupled ODEs. Indeed, this equation becomes I forgot the m here. No. du1 dt equal to u2. This is basically telling you du1 in the t is exactly the x in the t, so this is equal to u2, which is correct. And the other one, which is du2 in the t equal to minus k over m u1. So you will have first a linear system of coupled first order ordinary differential equations. I don't know if you're used to this or not. We can have a pause if you want. We can have a break of a couple of minutes. Wow, surprising. All right, come on, break of a couple of minutes.
Quanto tempo di pausa?
5 minuti, 4 minuti.
How much are you paying?
4 or 5 minutes, yeah. You have time for coffee if you want. Yeah. Come sta cosa? Non siete abituati a fare pausa?
No, perché tanto alla fine un'ora, cos'è, dalle 2 alle 4.
Sì,
Quindi di solito quando...
si porta avanti.
Esatto. Sì, oppure di solito si finisce un quarto d'ora prima.
No, ma preferite voi?
No, la pausa giustamente recuperiamo.
Se preferite venire un quarto d'ora prima, va benissimo.
Sì, esatto.
Non è
Bene.
46, non è 46.
Sì,
Va bene, va bene. Come preferite voi?
Poi magari ci devono se le registriamo queste anche online, cioè ci stanno registrando i...
Credo di no, ma hanno detto che non si devono registrare.
Ah, non si possono registrare.
Ma hanno detto che no.
Cioè, a scambio di calore le registriamo. Vabbè.
Io semplicemente seguo le istruzioni che mi danno e mi hanno detto di registrare. Vabbè.
Secondo me, ragazzi, quando è tornato la formulazione della formula di Google, diciamo magari quando l'attenzione, come modo di magari la trasfigurazione su.
Non ho capito sinceramente a un certo punto che cosa si riferisce.
Damage non so
Damage danno, no?
io.
Non so. Urto, magari parlava degli urti, non so.
Io non c'ho più questa mascherina.
Sia andare che venire, perché guardate dall'altra parte.
No, non c'era, ma la mattina non vedo se c'era. Magari studiare ritorno adesso. Cioè, spiegare di cosa non so, non vedo. Sto scherzando. Così le slide sono già disponibili sul web?
Queste?
No, io sul slide.
Di che slide sta parlando?
No, giocare nel corso.
Allora, guarda, il corso c'è una pagina aula web dove però al momento non c'è niente. Come dicevo questa cosa non c'è. Sì? Yeah? Su aula web penso di mettere queste, però sono scritte a mano. Oddio, non sono tanto male, voglio dire, non credo che siano, cioè è scritto meglio di questo, perché questo è un po' difficile. però spero si capisca. Però davvero sono semplicemente una revisione di quelle cose che stanno su quel libro di Bellomo e Tal. Oddio, il libro di Bellomo e Tal c'ha pure qualche erroruccio, queste cose così, quindi cerco pure di correggere sta roba. All right. All right, let's start again. What happened?
Si è cambiato sezione. Sì, una nuova sezione. 1, 2, 3.
No, questo l'ho fatto, sì, d'accordo. No, è su questo, è sulla parte del computer che non capisco. Vabbè.
Sei lì sulla...
Yeah. No, è con Teams, problema con Teams. I hope that you are still there.
Yes,
Oh, all right. Yeah. Is there any question there from home? No. All right. Great. Then let's move on. So in these other hours, what I would like to discuss is instead some the idea of some conservation law, balance law. Indeed, many mathematical models, especially those which are inherent to mechanics or to heat flow, can be derived using some kind of balance law, balance equation. So the idea is that if you have a certain quantity which is changing in a given domain, for example, in a given volume of your system, this change must be equal to the rate, at which the same quantity is flowing through the boundaries of the system. Let me give you a very, very simple example. Imagine that you are considering the population of some animals, right? So the rate at which the population of the animals is changing, so this P dot, must be equal to the number of animals that are created and destroyed in the region, which basically means birth rate plus death rate, plus the number of animals which are moving from the region toward, outside the region, and the other animals which instead are coming from outside the region inward. So basically you have to add the migration term, right? So again, this is that part of the quantity which has been destroyed or created inside the volume. This other part is that is telling you what's the flow of the quantity that you are studying, which is either going outside your volume or coming inside the volume. And this is telling you what's the rate at which your quantity is changing. So this kind of reasons of ideas is behind many mathematical models. Indeed, what I'm going to do now is to use this argument to find the heat equation. So what I want to do is to find heat equation for heat flow in a homogeneous isotropic and continuous rock. So basically, the idea is that I'm finding this equation in the three-dimensional expression, but then what I would like to do is to specify to the one-dimensional case. So my rod, the idea is that my rod then is going to be one-dimensional. In any case, we are going to do the calculation in 3D, and then we'll specify in 1D. So we can assume that when we are in three dimensions, at each point x of a solid and at each time t, there is an energy density E of x and t, such that the internal energy in a fixed region, a fixed volume V, so the heat of a given fixed volume is given by the integral on that volume of E x and t in the x. Now let me assume that there is also a heat flux vector Q of x and t, such that the rate of heat that is flowing through the boundaries of the region with volume V is given by the integral on the boundary of Qx and T scalar n in the S. N is the normal outgoing normal to the boundary. Okay. Now the idea that I have a conservation energy, so trying to write exactly the same kind of equation that I wrote here for the rate of change of the population of animals, is to say that the sum of the contribution of the internal energy and of the contribution which is given by the energy which is flowing instead from my volume V must be equal to 0. Then this means that the change, the sum of the change, the rate of change, so d in the t of the integral on the volume of E x and t in the x plus the integral on the boundary of the flux Q x and t scalar n the S, this is equal to 0. Now, I can rewrite the second term How can I write the second term? What's this thing here? Any idea? What's the term?
question. The step between the integral in the x, and then you put on the t. I lost this.
This is the rate of change. Actually, that's exactly the same thing that we've done here with the animals. So what I'm calculating now is how the energy is, what's the rate of change in energy, in internal energy, in heat of my system. So if the internal energy, the heat of the system is this one, the rate of change, so the rapidity, the velocity at which this energy is changing is day in the t of this quantity, right? Now, the day in the t of this quantity must be equal to what? To heat that has been created or annihilated in the system, which in this case is 0, plus migration part, which is basically the flux of heat which is given from this term, by this term here, the flux of heat through the boundaries of the system. So imagine that you have, in this case, it's a road. So I have this road, the road which is closed here and there. So this term here is the heat which is here inside. Then the T of this thing is how the heat is changing. And this term here is telling me how much heat is leaking from the road, from the water.
This law is of conservation of energy.
This is conservation of energy. Yeah, but how shall I rewrite this term here? So basically, you can use divergent theorem. Green's theorem, I don't know how you call it. Well, Green's theorem is 2 dimensions. In 3 dimensions is divergence theorem, which relates this quantity to the integral on the entire volume of the divergence of Q. What's the problem? All right. So I can rewrite this term here in this way here. Right? So I'm rewriting my equation in this way. Now, under the assumption that all my functions are well behaved, and note that when I'm speaking about well behaved functions, usually I'm speaking about smooth functions. So functions which has first derivative, at least the first derivative which is continuous. Okay. Under this assumption, what I can do is to move the derivative with respect to time inside the integral, and this becomes integral on the volume V of the partial derivative with respect to time, note which is a partial derivative because E is a function of both x and t. Partial derivative with respect to time of E, x, and t in the t. Plus divergence of q, x, and t, the x equal to 0. Now what I'm going to use is the arbitrariness that I have to choose my volume V, which basically means that if the volume V is completely arbitrary, this means that in order for this equation to be fulfilled, what should be equal to 0 is the integrand. So what should be equal to 0 is the derivative with respect to t of E, x, and t plus divergence of q, x, and t equal to 0. Okay? This is true because this equation here is true for any volume V. In order for being true for any volume V, this means that this quantity here must be equal to 0. Now, at this point, we are again in the situation of saying, fantastic, this is a very, very nice expression to which I can arrive just doing some reasonable, just thinking and using some maths. But now I need some experimental evidence which allows me to relate E to Q. And basically these experimental laws are the laws which indeed give me the possibility to express E as a function of the temperature and Q as a function of the temperature. Okay? These are what are called also constitutive relations. Now, these constitutive relations, again, are empirical relations, are relations that you must find doing experiments and observing the natural phenomena. For many materials, not all the materials, but for many materials, what you can show is that E, internal energy, the energy density, sorry, is actually proportional to temperature. This is indeed equal to rho, which is the density of the material, times well, a constant C, which is the specific heat capacity of a material, times the temperature, which is a function of X and T. On the other hand, I still have to express Q in terms of the temperature. Again, there is an empirical relation that I can find doing my observations, my empirical observations, my experiments, which tells me that the flux Q is proportional to the gradient of the temperature through a parameter which I'm calling K, which is the heat conduction. So it's minus K times the gradient of the temperature T of X and T again. Do you have any intuition of why there is this minus sign here? So what's the meaning of this minus sign? This is something that you can have an intuition of this if you are thinking about the two bodies with different temperature that are touching one to each other.
Because the temperature gradient is negative, and then the heat flow goes from the hotter body to the colder body.
Right, yeah.
Gradient,
That's correct. Actually, that's the idea. Yeah, exactly. Then, okay, now that I have these constitutive relations, what I have to do is to use the relation inside the equation, this equation that I found here. So I'm going to use these two equations, substituting these two relations in the equation 1. What do I find? Rho times C, rho and C are supposed to be constant for the moment, so rho times C times the derivative with respect to time of the temperature. Let me move the second term on the right hand side. This is equal to K times the Laplacian. It's nabla T of X and T. So let me go this, the Laplacian of T of X and T. All right? So this is what's called the heat equation. In particular, I promised you the idea was to specialize to the one dimension, but it is trivial because basically if I want to specialize one dimension, it means that this can be written as rho C derivative with respect to time of T of X and T equal to K, which multiplies the second derivative of t with respect to x squared. So this is the promised heat equation for my one-dimensional rod. What can I do with this equation here? Well, I can use, for example, the equation for trying to understand what happens for steady temperature. So for temperature which is not changing with time. If my temperature is not changing with time, this means that T of x and T reduced to some T of x, correct? But if I have just T of x, so steady temperature case. This one we're saying. So if T does not depend on time, this means that the left-hand side is going to be equal to 0. And the right-hand side reduced to an ordinary derivative. This is a total derivative. Second derivative of t of x with respect to x squared.
Not plus.
Then again, what we can do is to rewrite this equation, which is a second order equation, as a system of first order equation, correct? So what I can do is to rewrite this thing as some delta index, which is going to be some quantity that I'm going to dub capital V. And then this equation here that instead becomes the derivative of capital V with respect to x, which is equal to 0. So what I've done is to take a second order ordinary differential equation and I reduce it to a linear system of first order ordinary differential equation, coupled equations, because as you can see in the first equation there are both t, the variable t and v. We can think of we can think, for example, what up? No. Voi messaggi. Guys from the other side, guys from home, it would be better if you want to ask something, just ask it. I mean, open the microphone and ask it, because I'm really looking at the screen and I can miss some of the questions that you are writing on Teams. Okay. All right. Any questions so far? These things I think are easy enough and standard enough. So we can try to introduce some kind of extra complication in our model. The idea that I would like now to show is how we can introduce nonlinearities in our mathematical model. Okay, so suppose that now the heat flux coefficient depends on the temperature. So if you remember, the heat flux coefficient was this number k here that was supposed to be a constant, right? Now there are some material in which this thing is not a constant but depends on the temperature. So instead of having this k, this k is a k of t of x and t. Okay? So what happens in this case? Well, what I have to do is to recalculate this the equation number 1, which I will write again here. Derivative with respect to time of e of x and t plus of q x and t equal to 0. E is still equal to rho c times t. Oh well. And q now is equal to minus k of t times nabla t. Okay, now let's see what happens if I'm substituting this thing inside my equation. Okay, now the first part is going to be the same. So here we'll have the rho times c times the derivative with respect to time of e of x t of x and t. Then I have plus nabla of what? Of minus k of t of x and t times nabla t of x and t equal to 0. Okay, let's do calculation in the simple case of in the one-dimensional case. So let me drop. This is not a vector anymore. And this is also not a vector anymore. Right? And then this is a derivative. This becomes a derivative with respect to x. And also this is becoming a derivative with respect to x. So what happens? The equation now becomes rho c then the t of temperature of x and t. Then I have minus k times the second derivative with respect to x of t of x and t. Fair enough, that's exactly the same thing that we had before. And then I have minus the index of k of t times the index of t. The terms to which we have to pay attention is, of course, this last term here. Because now this thing here, what it is? It's the derivative of k with respect to the temperature T times derivative of T with respect to x. This is also multiplying the derivative of T with respect to x. This is the same. This is the same. So it ends up with the first two terms, which are exactly the same terms that you find when we are looking to the linear heat equation. And then I have this further term, which is the non-linear part, the k in the t times the t in the x squared. So this is the nonlinear term. As you can see, usually whenever you are abandoning the constraints of having some constant. So whenever you are allowing instead of having some coefficients that depends instead from the particular state variable that you are considering in your system, very probably you will end up with the mathematical model with the non-linear terms. Now, mathematical models which are linear are usually easy enough and treatable. Not necessarily always analytically solvable, but they are more treatable. When you start to have non-linearities, things becomes extremely more difficult. But we will discuss these things later in this course. Now, even with the basic knowledge of differential equations that you have, you should have shouted at me and protested a lot, because you should have recognized that actually in all these examples, I was missing an extremely important ingredient, right? Which are initial and boundary conditions. Indeed, in the first example that I showed, which was the examples of the body which is connecting to the spring and Hooke's law, basically that one was an ordinary differential equation which I arrived. But in order to solve that problem, in order to find a solution to that equation, what I need is some initial conditions. So I have to define my functions at some time t equal to t naught. In the same way, for the other two examples that I show for the heat equations, I should have given to you at least other two conditions. So one condition was the initial condition. So I need the profile of the temperature at the time t naught. And second, what I need is the boundary conditions. So I need the conditions, the profile of the temperature at the boundaries, when the road stops, or when, if I have some other kind of system in a sphere, I'm studying the heat of the sphere, I need to know what's the profile of the heat on the surface of the sphere. So in order to solve all these problems, it's absolutely necessary that I'm also assigning either initial conditions or both initial conditions and boundary conditions. And this is also another problem that we will study in the course of our lectures. Now, after these examples, let me finish the class with some identifying some definitions for the common elements of the problems that I showed today. Something that we have already touched at the beginning of the lecture. So in all these problems, what we can identify are, first of all, some independent variables. In the problems that we have seen, what are the independent variables? Time.
Spatial coordinates.
Spatial coordinates?
Density.
No,
No,
that's
not. It's a constant.
Somebody there? No. Actually, the independent variables, I'm cheating because the independent variables are just, in these problems, are just the time and the spatial coordinates. These are the variables with respect to which you are determining what is the evolution of your system, right? So you are describing the evolution of your systems in terms of these variables, 2, 3, or 4 variables. It depends on the number of spatial coordinates that you have. On top of this independent variable, we have defined another. We have defined another thing. What I called actually state variables. The state variables are basically the physical quantity with respect to which you are defining your problem. For example, in the case of the heat equation, the state variable, so the quantity of which I'm trying to define dynamics, I'm trying to define the profiles for this time and space, is the temperature. Okay. In the case of the spring and the mass, the state variable was itself the position of the block. Well, actually, with the position and the velocity of the block. So a state variable then can be defined as a finite dimensional vector, which I'm calling U, whose components are which is a function of time and space. So it's a function of which is taking time in the interval t naught to some time t, and which is taking values for x in some volume v, and is giving me some n-dimensional vector. So U is an n-dimensional vector, which I can write in this way. And this describes the evolution of the physical state of my system in terms of the independent variables, in terms of the variables t and x. Then at the end of the day, actually, what the mathematical model is a evolution equation which is suitable to define what is the evolution of the state variables which are contained in this vector U, so which is this vector U. My mathematical model is said to be consistent if the number of independent equations that I'm able to isolate is equal to the number of independent components that I have in the state variable.
Can you repeat this?
Yes. So the mathematical model, the model is said to be consistent if I'm able to find a number of equations, which is equal to this number of components of the state variable. So, for example, just a second, just to conclude one thing. For example, in the case of the mass connected with the spring, where my state variables was is this u, which includes both the velocity and the position of the mass. The two independent equations that I have are this and this. These are two independent equations. So this means that the number of equations is equal to this number of components of my state variables, and this allows me to say that the system is consistent. Please.
You mean what are you told us about what you told us, the system of KLM?
System of KLM.
Yes, there is a system of when something is related to for this distance.
I don't understand what you are referring to, actually.
The system of KLM, when something is related to the length, the distance, should be meter. When something is related to the base, it should be m.
Frankly speaking, I didn't get the question, but we can discuss this later if you want, in a moment, because actually I think that for today, it's it's over. So thanks a lot, and we can have next lecture tomorrow. All right? You can come if you want. You can come and you can come. Yeah, tell me. I didn't understand what it was.
System of key and
Okay.
that is a system and want something maybe that is mass relate for this that should be bring some maybe the first step of Newton. Let's say
You can write here.
Thank you, Professor.
Thank you to all. Thanks. Cheers. See you tomorrow. You can write.
this maybe.
Thank you, sir.
Thank you, Professor. Thank you.
Maybe.
Guys, now.
Oh,
Actually, it's, the idea of the course is to try to have an idea of how to solve partial differential equations with coordinate differentiation. We know the possible tools that are easy to be described from the theoretical point of view, because usually partial differential systems or PDEs and ODEs, you solve it mathematically. Because you have a number of methods that you can use to solve them empirically, or trying to have some easy to write calculate numerical methods, but mostly you are solving as computer applications.
There is this course because I have a team.
You don't have the things.
Yes, I have a team, but I don't have this.
Oh, but they put the code of the course on our web. Yes, you go on our web and you can find the code of the course.
Okay.
Okay.
All these, the file.
The file, okay, this I don't think is gonna be on the our web, but I will put my notes. Okay, my written. Ciao. Ciao. Okay. Cheers. Ciao. Ciao. Ciao.
Not for the same course, the same course of Easter last year.
No, no.
It is different.
It's gonna be a bit different. Yes, with respect to last year.
Last year, not like this year, the system.
No. It's gonna be different. Yes.
Yes. Okay.
Also because I decided to do it in another way, to follow another approach.
Yes, because last year you are not you to.
No, I just arrived. I arrived a couple of months ago.
Va bene. Ok, grazie.
Okay,
Ciao.
cheers. Boh, ma io non sto registrando.